Hey guys, this is Srini and you're watching Python tutorials on my YouTube channel, Python for Microscopists. In the previous tutorial, I talked about the theory behind linear regression. And in this tutorial, let's actually write a few lines of code for this linear regression. Now, please watch the previous tutorial, but for those of you who are busy, let me actually cover the summary of linear regression in the next couple of minutes, and then we can jump on to the coding part. Okay. For that, let me switch to the drawing board here. And the example I've used in the previous tutorial was, okay, as the time ticks, okay? So on x-axis, we have time. And on y-axis, we have the result of an experiment that we are performing. In this case, in this example, I'm saying, okay, I have number of cells, and the number of cells is growing are growing as a function of time. Okay, this is just an example. Other examples, and by the way, the time here is the independent variable because it's not dependent on anything in this experiment at least, and the number of cells are dependent on time, right? So as the time changes, the number of cells actually grow. Now, in real situation, the number of cells or whatever that dependent variable is can be dependent on multiple variables or multiple independent variables, time, maybe temperature, right? So as you change the temperature, the number of cells either grow fast or small or slow. So in real life, there may be multiple variables, and let's store that, save that for the next tutorial where I talk about multiple linear regression. But for now, let's just say, okay, we have one independent variable and one dependent variable, right? So this is the number. So if you plot it out, you start off with a number, okay? So when you actually have your initial state, let's say you have 100 cells. But as the time goes by, the number of cells actually changes, and they're never in a straight line in reality. So it may look somewhat like this. Now, the reason for linear regression is to fit this data to a straight line. So that's exactly what linear regression means. Let's say I want to start with the initial point and then fit a straight line. That looks like a decent line, right? A bad line would be, okay, if you want to draw something like that, that is a bad linear regression because that line does not represent the data very well. Okay, so linear regression is all about how well this line represent the data, meaning minimizing this error between the observed data and the predicted data. Okay, and the output of linear regression is nothing but a straight line, and straight line is defined by an equation called y, let's say y equals mx plus c. Again, depending on where you got educated, you may be using terms like y equals ax plus b or b1x plus b2 or something. Yeah, so it's nothing but one constant for slope and one for intercept, right? So this is your intercept, this is your c, and the slope here, the right there, this is your m. So linear regression again is nothing but predicting a straight line that represents the data very well. And why do you want to do that? When you put a different sample, so probably you can compare the two samples, or you can forecast how the experiment is going to be, how the number of cells are going to be at a specific amount of time. So there are various reasons. Another example, if you're a material scientist, on the x-axis you have grain size, let's say of D. On y-axis, you have the strength of the material. As you probably know, the strength of the material is a function of the grain size. So in fact, it's a square root right there, but it doesn't matter. So let's say there is a linear relationship between two parameters and one independent, one dependent. So this is linear regression. So now that we understand what it is, let's jump into the code, into coding, and look at some data. And in fact, the data that I have, let's have a quick look at the data, is exactly sticking with the same example. On x-axis, I have time going from 0 all the way to 5 hours, incremental of half an hour, let's say. And then I'm just counting the number of cells at every half an hour. So this is the data. I want to fit this to a straight line. So let's go ahead and start coding. Okay, and for coding, I'm going to use Spider interface. Again, on the left-hand side, I can write my code, and the right-hand side in the console, I can look at the output. Okay, I don't want to go through the Spider console again. So let's import, first of all the required libraries. As usual, all the data is handled using pandas library. Okay, so let's go ahead and start pandas as PD. Okay, we may as well import other relevant libraries. Again, I'm not sure if I'm going to use this, but let's go ahead and import it. If not, I can delete it later. And we may as well plot. So matplotlib, hopefully you remember this, .pyplot. Let's import that as PLT. Okay, that lets us do any plotting if we need it. Now, how do we again do this linear regression? So the library is from Rsquared Learn. Sci-Kit Learn has a lot of tools, for machine learning, and we are starting again this baby steps with linear regression. So what do we import from Sci-Kit Learn? Let's actually import linear model. Okay, so these are, at least for now, the libraries I can think of. And if we need more, we'll add them as needed. So from pandas, step number one is reading the file. So I'm going to define, again, this is the convention. My data frame is nothing but I'm going to read a CSV file. Okay, so the file that I just showed you was a CSV file, and it's called cells.csv. Okay, so this is the file I'm going to read, and just to make sure we got everything okay, let's go ahead and print it. Well, there you go. So as you can see, this is my original CSV file. On x-axis I have time, on the column A I have time, column B I have cells, and they got imported right here. So on the total I have 10 data sets. Okay, now if you want to look at how it looks like, is it really a straight line? Does it look like a straight line? Okay, so let's actually, since we imported our matplotlib, let's go ahead and plot uh, let's do it the right way. So label my x-axis as time, and let's label the y-axis as cells. Okay, and now let's go ahead and do a scatter plot, and which data from data frame I want time, and from data frame I want my cells column. Okay, and let's color them in red, and again I'm just also including a little bit of pyplot tutorials as part of this, and let's go ahead and set our marker to plus so it's easy to see. Now let's go ahead and execute this, and as you can see, this is how our data looks like. It's not really, like along a straight line. I see them grow faster here, the number of cells, and then at a different slope, and then at a different slope right there. So our goal is to fit a straight line through this data. So again, doing this linear regression is literally straightforward. Step number one, we need to create the instance of the model. I'll explain what that means in a minute. And then we need to fit, which means train the model or fit a linear model, and then we need to predict on a bunch of unknown values. So let's start by defining, first of all, let me delete or at least comment these parts out, and let's start by defining what our x is and what our y is. Yeah, x is always the independent variable. Okay, again, comment x independent. In our case, x is time. Okay, and y is the one that we need to predict. Yeah, dependent, we are predicting y. Okay, so how do we define our x? Well, a couple of ways. First of all, let's define x underscore my data frame, a new data frame, and there are two ways. Basically, I'm trying to pick what our x is. In this example, there is only one x, right? Time. As I mentioned earlier, there could be multiple independent variables. That's why x is a data frame of any number of independent variables. So since we have only one, the one easiest way to do this is to drop the cells column. Okay, remember again, please go through the pandas tutorial that I covered a few lectures ago, how to pick, select certain columns, how to drop the columns, and so on. So I'm going to drop the cells column, and the way you do that is axis equals columns, I think. Let's see. So this is going to define our x as whatever this data frame minus the cells column, which is nothing but the time column. Okay, so if you want, you can just look at print x right there, and let's go ahead and run it. So you can see now my x is only the time. Okay, the other way, I said you can define this couple of ways, right? So I'm not gonna let me just go ahead and show it. So the other way to do that is x data frame equals to just define your data frame, and instead of dropping, you just pick whatever you want. Yeah, so this is it. So you just pick that. Okay, let me go ahead and comment this out and run it. So you see that the output should look exactly the same. And by the way, remember to put these double brackets, okay? Because the double indicates that this is a data frame, and if you only put a single one, let's go ahead and do that, then this is going to be a series. You see there is no column name here. Here you have time, there is no column name. Let's actually do one thing. I don't want to take big detours, but this is very important. Let's actually go ahead and print the data type, x underscore df dot d types. Okay, so now instead of doing that, let's go ahead and print the data type. You see how it says float 64? This needs to be an object. So if I put double brackets here and run this, it should say data type is an object. Okay, that's when you know that okay, this is working okay. In fact, if I comment this out and go back to the other way where we dropped the columns, I should see that this is an object again. Okay, just a side note, I've done that mistake of putting one square bracket initially when I was trying to do this almost for the first time, and it drove me crazy why it wasn't working. So uh, okay, so we defined our x. Let me remove this so I can keep the code clean. So now we need to define our y, and y is pretty much easy, which is we just pick one, which is our cells, right? So this is our y. Now so far we just defined what our x is and what our y is, and now let's actually create the model instance. So okay, so my uh, linear, remember, linear underscore model, okay, dot. Now you can see a whole bunch of functions within this. So what we want, we'll also talk about logistic regression in one of the other tutorials later on, but we want linear regression, linear model dot linear regression. In fact, when you import it, you could have done that right here from Sci-Kit Learn import import linear model dot. You can actually import the whole thing, so you don't have to do linear model every time. But anyway, uh, that's it. So what this does is it actually creates an instance of the model. Okay, so now that we created an instance, now I just need to fit the data. Okay, so the way you do that is, I mean, I could have called this anything, right? I can call this model. I just called it reg. That's what I typically use. So model.fit or whatever, reg.fit. Fit to what? My x data is x underscore df, y is y underscore df, right? So this is it. So this is basically your, by the way, this is nothing but training the model or fitting, fitting a line to the data. That's pretty much it. So that's why I say this is very underwhelming, doing the actual coding. All you got to do is, where is my data frame? What is my x in the data frame? What is my y in the data frame? And then create an instance for the model. In this case, it's linear regression. It could be anything. It could be any of these machine learning models. The structure is the same. You create a model and you fit the data. So, and the next step is, I mean, we can go ahead and predict, but actually, let's go ahead and predict this. Okay, so let's say, okay, I want to directly print, let's say predicted, let's say number of cells for a given, let's say, what do we want to do? So the way you do prediction is the model dot predict. Okay, and that's it, dot predict. So now for what values do I want to predict? For now, let's just say a value of 2.3. Okay, so we have 2.5 as 260, right? So I'm just using 2.3. So hopefully it should be somewhere around 260 between 248 and 260. So that's why I just picked this. So let's go ahead and run it. So predicted number of cells is 257.6. As you can see, it's pretty close to 260. So now we know that, hey, it's working very well. A better way of finding out if it is working very well is there is something called dot score. So let's go ahead and print reg dot score. And again, for what? X underscore df and y underscore df. Okay, so this actually predicts the score. Let's go ahead and print this. Do not print this. So it should print the R-squared value. It says 0.978. I mean, a value of 1 means the data fits very well. Okay, so this is nothing but an R-squared value, which is a measure of how well the observed values, yeah, are replicated by the model. So this is basically a measure of good fit, between the initial original data and the predicted straight line. This is it. This is how easy it is to do linear regression. And by the way, linear regression, like I mentioned, it's nothing but fitting a straight line. So if you really want to know, I mentioned that this is y equals mx plus c, right? So if you want to know what the equation is or what the slope and intercept is, you can basically uh, uh, do intercept. So this returns the intercept value to you, and then let's call our m equals, it's COEF underscore. There you go, right there. Okay, so this actually gives you the value. So again, let's keep this example of 2.3, and let's say let's do something fun. Print uh, from manual calculation. Okay, I don't know. I cannot think of any better way to say this. My number of cells is equal to what? So now let's actually, because we have m value, m times what's the input? 2.3 plus, or what did I call, c, right? Okay, so let's go ahead and print this, and hopefully we should get the same number. Let's do that, and let's comment this out. Anyway, in case you're wondering, all I'm trying to do is basically show that this dot predict 2.3 is same as this value, and hopefully we'll find that out. Okay, so you see 257.61 exactly identically the same value. Yeah, so all I'm doing is just printing out what the slope and intercept is, and when you do predict in the background, that's exactly what it's using. Okay, so this is it. This is our linear regression, and I was thinking whether let's actually finish this off. Let's make this even better. So what if, I mean, very rarely do you want to predict something for one single value, right? So you probably have a CSV file that has a bunch of values for X, and you just want to predict Y. So how can you do that? So let's go ahead and do that exercise in the next couple of minutes. So our goal here is to take in a whole bunch of X values and then print out corresponding Y values. Yeah, now that we actually fit a curve or a straight line to it. So I already created a CSV file. I think it's this one with a whole bunch of, it's nothing but just one column, okay, time, all the way from 0.1 to 4 with the finer steps. In our original data, I think it's every half an hour. 0, 0.51, and now I actually broken it down to zero point 0.1, 0.2, all the way to 4. I try not to extend, again, I try not to extend the data beyond the original data. Let me go back again. Because my data goes from time 0 to 5, I don't want to predict something that is time 10 because that's extrapolating it too much. Okay, that usually doesn't work very well. Even if it is 5.5, I get a bit uncomfortable. I try to interpolate but not much extrapolate. Okay, so now our goal is to add another column to this with the predicted values for each of this X value there. Okay, step number 1. Let me go ahead and create some room. Step number 1 is reading our file. So again, so cells, let's call it predict df equal to read CSV, read CSV, and my file name is, I need to verify this one more time, cells underscore predict. Okay. Okay, so now that we have, let me close this. Okay. So now that we have this file, let's go ahead and make sure we are actually reading it correctly. So you know how to do this. Cells underscore predict df, and let's only look at the top view. Okay, and that's pretty much it. Let's print it. There you go. So we just have, time 0.12345. So we're reading it okay. Now, you know how to predict, right? Predicted cells equals to our model. Okay, I called it reg dot predict. That's it. Predict on what? Cells underscore predict df. That's it. It's as simple as this. So now it's going to predict the y values for all of these x values. Okay, let's go ahead and print them out first before doing anything else, just to make sure again. Predicted underscore cells. So let's go ahead and run this whole thing, and obviously we got some numbers right there. Okay, just to see 0.1, 212. If you look at the input number, 0 is 205, and after half an hour or 0.5 you have 225. So 212 seems to be pretty good. So so now that we have the prediction, let's go ahead and add this as a new column. So cells predict data frame. I'm going to add another column called cells. Okay, again, I covered this as part of pandas. So all we're doing is adding another column, and where are the values for that column? Coming from predicted underscore cells. Okay, so you can print the data frame to see if it looks okay. Cells underscore predict data frame. So let's go ahead and print it. So the last thing we should see, there you go, the data frame. So where you have the time, where you have the corresponding cells. That's it. All we need to, I mean, if you like this as a CSV, again, this is pretty simple, right? I mean, cells predict data frame, and you know how to do to CSVs. It's CSV. Okay, that's it. And what do you want to call this? Let's call this predicted cells. I'm running out of names here. Predicted cells dot CSV. I hope you're more organized when it comes to name. Uh, okay, so there you go. So I'm gonna run it, and let's go ahead and open the file. There should be a new file called predicted cells dot CSV. So let's open that. Well, I double clicked. We should see that any second now. There you go. There you go. So here is the new CSV file that has both the time and the number of cells. I hope you found this tutorial useful. So what, again, let me quickly summarize this. It's very important, okay? So we have a bunch of data from our experiment in this example, and we think that this should fit to a straight line. So we assume that, okay, y equals mx plus c. This is our straight line, and x-axis is time, y-axis is number of cells. So in our code, we defined our X data frame by dropping the column called cells. So it only leaves the time. Yeah, it only leaves the time if we drop the cells. And our Y data frame is nothing but the cells itself, okay, the number of cells. And then we just created a model using linear regression, and we fit using x and y values that we just defined up here. That is pretty much it. Now it defined a straight line. How do we know it defined a straight line? You can actually extract the slope and intercept values if you want, and we tested that out. Okay, and once you fit a model, you can predict the values. I mean the y values for any given x. In this example, dot predict, we predicted for 2.3. Down here we predicted where is it? Right there. We predicted for a entire data frame that has a bunch of values under, and those values are, we obtained them by reading a CSV file. So this is pretty much it. And instead of making this tutorial very long, let me actually break it down into two. In the next tutorial, I plan on actually covering how to actually take a subset of your input data and break it down into a training data set and a testing data set. So that way you right away know that, hey, based on your training data set or testing data set, you can look at your accuracy right away. Okay, that's the actual true way of doing machine learning. So let me cover that in the next tutorial. So please like this tutorial if you found this useful. If you find this series of videos useful, please subscribe to my channel, and let's meet in the next tutorial. Thank you very much.